Hello everyone, I am Professor Amit Thakur. In this session, we are going to discuss about operations in heap tree. In this session, we are going to cover following topics like what is heap tree, key characteristics of heap trees, key operations performed on heap trees, where and when to use heap tree, and heap tree applications in real life. So, after this session, the learning objective of this session would be, after this session you will be able to learn what is heap tree. We can discuss about the key characteristics of heap tree, what are the key operations we can perform on heap tree, and where and when to use heap tree, and rest of the application of heap tree. So, we will discuss about this objectives. So, first of all we talk about what is heap tree. A heap tree, often referred as simply as a heap, is a specialized data structure that is used to maintain a partially ordered of elements. It is commonly implemented as binary tree, especially as a complete binary tree, and it satisfies the heap properties. The concept of heap, which is a type of binary tree structure used to implement priority queues and other efficient algorithm, has been around in computer science for a long time. It is not attributed to a single developer or inventor. The heap data structure and the related algorithm have evolved over the years through the contribution of various researchers and computer scientists. The heap data structure is a fundamental concept in computer science and algorithm, and its development can be traced back to various historical sources and research papers. It is a part of fundamental knowledge, and the most computer scientists and algorithm designers learn as they study data structure and algorithm. While there might not be a single developer of this heap tree, you can give credit to many pioneers in the field of the computer science who contributed to its development through research, publication and education. Some notable names in this field of this binary heap tree is known as Donald Knuth, Edgar Dijkstra, Robert Floyd and many more. It is important to recognize that many concepts in computer science, including data structures like heap tree, are the result of collaborative efforts and iterative developments over the time. As a result, attributing the development of heap tree to a single person would not accurately represent the collaborative nature of the field. The heap property dictates the order and relationship between elements in the heap and can be of two types. Basically, we can broadly we can classify into two types. The first type is mean heap and second is max heap. Now, first we will talk about what is mean heap. In mean heap, for every node x with parent p, the value of p is less than or equal to the value of x. In other words, the smallest element is the root, and for any node in the heap, its value is greater than or equal to the value of its children. Now, we can see what is max heap. In max heap, for every node x with parent p, the value of p is greater than or equal to the value of x. This means that the largest element is at the root, and for any node in the heap, its value is less than or equal to the value of its children. Heap trees are often used to implement priority queues and to efficiently solve the problems where the elements need to be processed in order to their priority or value. Now, we will discuss about the key characteristics of this heap trees. The first characteristics or property is complete binary tree. Heap trees are typically implemented as complete binary tree. This means that all levels of the trees are filled except possibly the last level, which is filled from the left to right. The property allows for efficient storage and access of elements using array. The next property of heap tree would be heapify operations. The process of creating a heap from an array is known as heapification or heapify operation. It involves starting from the middle of the array because of half of the node are left nodes and trivial steps by themselves, and then repeatedly bubbling down each elements to establish their heap property. Now, we discuss about the next property is efficient operation. Heap trees enable efficient operations like insertion, deletions and retrieval of highest or lowest priority element. These operations have time complexity like capital O log of n where n is the number of elements in the heap. The next property is not a sorted structure. It is important to note that the heap property does not enforce or sorted order between this sibling nodes. It only maintains a relationship between parent and child node. As a result, while the root of mean heap contains the smallest element and the root of the max heap contains the largest element, the ordering among the elements within the same level of the tree is not guaranteed. In summarize, or we can summarize like a heap tree is a specialized binary tree data structure with either the mean heap or max heap property. It allows efficient priority based operations and commonly used in scenario where you need to manage and access the element based upon their relative priority of the value. Now, we will discuss about the key operations we can perform on heap tree. The following operations we can perform, like first operation like insertion, deletion, pick, heapify, change priority and merging heaps and many more. Now, we will talk about this first insertion operation. When you insert an element into heap, it is typically added as a new leaf node, preserving the complete binary tree property and then its bubbling up or we can say the pre-corroded up and the tree until the heap property is satisfied. In mean heap, the means it means the comparing the new elements with its parents and swapping its necessary until the parent is smaller than the new element. Now, we will discuss about this what is deletion operation in heap. The root element of the heap, which is smallest element in the mean heap or the largest element in the max heap, is removed. After removal, the last element in the heap is removed to be root position to maintain the complete binary tree property. Then this element is bubbled down or we can say is pre-corroded down the tree by comparing it with children or swapped with the smaller element or larger element in the heap. The third operation we can perform on heap is pick. The operation involves looking at the root element of the heap without removing it, and it is usual when you want to access the element with the highest or lowest priority without altering the help structure or heap structure. The next operation we can perform is heapify. Converting an array of element into heap is known as heapification or heapify. It involves starting from the middle of the array or we can say leaves are already heaped by themselves and performing the bubble down operation on each element to establish the heap property. The next operation we can perform is change priority. If the priority of element in the heap changes, you might need to adjust the position in the heap to maintain the heap property. This usually involves a combination of bubble up and bubble down operation. The next operation we can perform is merging heaps. If you had two heaps and want to combine them into a single heap, this can be achieved through merging. The simplest approach is concatenate these two heaps array and run the heapify operation to ensure the heap property is maintained. Remember, the heap operation have time complexity that depends upon the height of the heap tree, which is logarithmic with respect to number of elements in the heap. This property is what makes heap element or heap element is more efficient for priority queue than implementation and other algorithms for the that require efficient insertion, deletion and retrieval of highest or lowest priority element. Now, in detail we can see like insertion operation, how we perform insertion operation in heap tree. So, this will tell us in detail like insertion into a heap tree involves adding a new element to the heap while maintaining the heap property. This typically involves the process called bubbling up or we can call this percolating up, where the new inserted element is compared with its parent and swapped if necessary to restore the heap property. Here some step by step algorithm for insertion into max heap. The first step we can follow like add the new element as the last node in the heap, and the second step is compare the value of the newly added elements with the value of its parents. For example, the element at index minus 1 divided by 2, where index is the index of the newly added element. The third step we can follow like if the value of newly added element is greater than the value of its parent, swap to these two elements. Next step we can follow, repeat the comparison and potential swap with the parent element until the heap property is satisfied. That is, the new added element is smaller than its parents has been reached out. So, these are the steps we must follow, and this algorithm ensures that the newly added or newly inserted element is properly placed into the heap, maintaining the max heap property. The time complexity for this insertion operation is big O log of n, where n is the number of elements in the heap, since the height of heap is logarithmic with respect to the number of elements. Now, we will move to the deletion operation. We will see in detail, like deletion from the heap tree involves removing an element from the heap while maintaining the heap property. The element that is typically removed is the root element, either the minimum in a mean heap or the maximum or in max heap. After removal, the last element in the heap is moved to the root position, and then it's bubbling down and percolated down by comparing it with children and swapping with the larger element in the heap, or we can say the smaller child with until the heap property is satisfied. Here are some steps we need to follow to delete the element from the heap. The first step is replace the root element, then second step is compare the value of new added element with the values of its children. That is, the element at indices 2 into index plus 1 and 2 into indices plus 2, where index is the index of the new root element. Step 3 is, if value of new root element is smaller than either of its children, then swap it with the larger child. The next step we can follow is repeat the comparison and potential swap with child until the heap property is satisfied. That is, the new root element is larger than both of its children or has no children left. This algorithm ensures the heap property is maintained after the deletion operation. The time complexity for this deletion operation is big O log of n, where n is the number of elements in the heap, since the height of heap is logarithmic with respect to the number of elements. Now, we will move to the peak operation in heap tree in detail. The peak operation in heap tree involves retrieving the value of the root element without removing it from the heap. Since the root of heap tree contains the highest, or we can say in max heap, or the lowest in mean heap priority element, picking allows you to access the element without altering the heap structure. The algorithm for pick is relatively straightforward. The first step is, if the heap is empty, return an appropriate value, that is null, for example null, and second step, return the value of the root element. So, these two steps are need to be followed. The time complexity for this peak operation is constant time, that is big O of 1, and it involves directly accessing the root element of the heap. Keep in mind that this operation does not modify the heap or making it very efficient for quickly checking the highest or the lowest priority element in a priority queue scenario. The next operation we can discuss over here is heapify in heap tree in detailed manner. Heapify or heapification is a process of converting an array of elements into a heap, especially a binary heap, or we can say minimum heap or maximum heap. The algorithm involves iterative bubbling down each element starting from the middle of the array to the beginning to ensure that the heap properties satisfy for the all elements. Here are some step by step algorithm to heapifying an array into max heap. The first step we need to follow is start from the last non-leaf node in the array. The index of the last non-leaf node is length of array, that length of array minus 1 divided by 2. The second step is, for each node compare its value with the value of its children if any exist or if they exist. The third step we need to follow is, if the value of node is smaller than either of its children, then swap it with the larger child. This is the third step. And the fourth step, after swapping, continue the process recursively for swapping child node until the heap properties satisfy. So, this has recursive process involved in step 4. Step 5, repeat the process for all nodes working your way up to the root of the heap. To perform the initial heapification or heapify on the array, you would iterate over all non-leaf nodes or in reverse order and apply the max heapify algorithm to apply to each of them. The time complexity of heapify operation is big O of n, where n is the number of elements in the array, as each element is like processed only once during the heapification process. Though, so complexity would be capital O of n. Now, we will see the change priority in heap tree in detail. Changing in the heap priority of the value an element is a heap tree while maintaining the heapify operation or heapify property involves two steps. The first step is you need to find the element to be changed, and then you need to adjust its position in the heap of the heap by potentially bubbling up or bubbling down the element until the heap property is satisfied or restored. Here how you can do it, like we have set certain steps. The first step is find the element. The first step, like locate the element in the heap that you want to change the priority of. You might need to traverse the heap to find the index of the element based on its value. The first step is to find the element. Second step is change the priority. Once you have the index of the element, change its value to the new priority. Now, we will discuss about third step, that is adjust position. After changing the priority, compare the elements with its parents and children if any. Depending upon whether the heap is max heap or min heap, you might need to swap the element with its parent if this priority violates the heap property. If element's priority is now higher for max heap or lower for min heap than its parents, then swap it with the parent and continue checking this process further up to tree. This algorithm the first performs a bubble up operation and then calls the max heapify function to handle any bubble down operation that might be necessary. The time complexity of this operation depends upon the highest of the tree, which is logarithmic in the number of elements, making it efficient. Now, the next operation we can see the merging heap in detail in heap tree. Merging two heaps involves the combining two heaps into a single heap while maintaining the heap property. One approach to merging heap is to concatenate two heaps array and then perform a heapification operation to ensure that the heap property is satisfied. Here we have certain steps that need to be followed. The first step is concatenate array. Concatenate two arrays representing the max heap you want to merge. Second step is heapification or heapify. Apply the heapify operation to the merged array to establish the heap properties. Start from the this last non-leaf node and iterate it reverse order, calling the heapify algorithm on each node. Keep in mind that this approach has time complexity of big O of n, where n is the total number of elements in the merged heap, means total array of elements. The initial concatenation steps like takes order of n times, and subsequent heapify steps also takes order of n time. There are more efficient merging techniques available, such as like using a specialized data structure. There are number of data structures available like Fibonacci heaps or Fibonacci heaps sometimes, but basic approach describes here is often sufficient for a small to moderately sized heap. Now, we will discuss about where we can use this heap tree data structure. The heap tree data structure, especially binary heaps, are commonly used in various applications where efficient priority based on operations are required. Their ability to maintain the highest or lowest priority element at the root of the heap makes them useful for solving the wide range of problems. Here are some areas where you can heap tree are frequently utilized. The first area is priority queue. Heap trees are the foundation for this implementing priority queue. A priority queue is data structure where elements are stored based on their priority and can be efficiently removed in the order of their priority. Heap based priority queues are widely used in algorithms like Dijkstra algorithm, shortest path algorithm, Prim's minimum spanning tree algorithm, and many more. Second, this area where we can use is task scheduling. In task scheduling algorithm, heap trees can be employed to efficiently manage a queue of tasks or like processes with different priorities. Real-time operations system, real-time operating systems often use this heap based rescheduling to ensure that the tasks with higher priority are executed first. The next area is online algorithm. We are dealing with data streaming or dynamic data sets. Heap trees can be used to maintain the top k or the largest or smallest element efficiently without storing the entire data set in memory. The next area where we can apply this heap tree is selection algorithm. Heap trees can be used to solve the kth largest or smallest element problem efficiently. This heap allows you to quickly identify the kth largest or smallest element without sorting or without arranging the entire array. The next element, the next area where we can apply this heap tree is event driven simulation. In simulation, an event driven system, the heap trees can manage a queue of event based on their this schedule time. The event with the earliest time can be efficiently retrieved and processed. The next area is Huffman coding. Heap tree are used in Huffman coding, a compression algorithm that assigns variable length codes to the character based on their frequency of occurrence. The heap helps build on this optimal prefix free encoding scheme. The next area is merge sort or external sorting. Heap trees are used in merge sort, step for merging sorting algorithms and external sorting algorithms. They help merge multiple sorted sequence efficiently. The next area is like median maintenance. In algorithm that requires maintaining a running median of a sequence of number of times, the heap trees can be used to quickly retrieve the median element. Graph algorithm. The heap trees can be used in graph algorithm like A star search for finding the shortest path in graph while considering estimated cost. Next is data compression. Heap trees are utilized in various compression algorithms such as Borrow-Wheeler transform like BWT, which pre-processes the input data to make it more compressible. There are just few examples of where heap trees are applied. In general, any scenario where you need to efficiently insertion, deletion or retrieval of element based on the priority of value could be potentially benefit from using this heap tree. Now, we will discuss about when to use heap tree. Heap tree, particularly this is a binary heap tree, are used in a situation where efficient priority based operations are required. Here are some scenario where using a heap tree is advantages. The first is priority queue. The most common use case for heap trees is in implementing priority queues. If you need to maintain a collection of elements with varying priorities and perform operations like insertion, deletion and retrieval of highest or sometimes we can say lowest priority element efficiently, a heap based priority queue is great choice. Second is Dijkstra algorithm. When finding the shortest path in a graph using Dijkstra algorithm, a heap based priority queue can be very helpful and efficiently extract the vertex with smallest distance from the source. Prim's algorithm. Similarly, when constructing a minimum spanning tree using a Prim's algorithm, a heap based priority queue can help you to choose the next edge with the smallest weight efficiently. Next is event scheduling. In simulation or event driven systems, a heap can be used to schedule and manage events in chronological order, allowing you to process events in correct order of occurrence. Top k queries. If you need to find the k largest or k smallest element from the data set efficiently, using a heap tree can help you to maintain and retrieve these elements without sorting the entire data set. Median maintenance. When you want to efficiently maintain the median of streaming data, a heap based approach can be used to keep track of elements larger than the current median and the elements smaller than the current median. Next is data compression. In various compression algorithms, heap trees are used to build optimal encoding schemes such as Huffman coding. Online algorithm. In scenario where you are dealing with like incoming data and need to make decisions in real life, heap trees can help maintain our important data points efficiently. Task scheduling. If you are working with a system that involves scheduling of tasks or jobs with different priorities, heap based scheduling can help to ensure that higher priority tasks are executed first. Graph algorithm. Heap trees can be employed in various graph algorithms where efficient management of vertices and edges based on their priority is required. In general, heap trees are useful whenever you need to manage and manipulate a collection of elements based on their priority or values in an efficient manner. They excel at operations like insertion, deletion and retrieval of highest or lowest priority elements, making them a powerful tool in various algorithmic applications. Now, we can compare this heap tree with the other data structure. Heap tree have their own strength and weaknesses compared to other data structure. The suitability of heap tree versus other data structures depends upon the specific problem you are trying to solve and the operations you need to perform frequently. Heap trees excel at priority based operations like insertion, deletion and retrieval with a good time complexity like order of log of n. And next is linked lists are generally slower for priority based operations, but they can be efficient for linear access or dynamic resizing. Heap trees are often faster for priority based insertion and deletion, that is order of log of n, compared to the balanced tree which is having slightly higher constants. Balanced trees provide more flexibility and can support additional operations like range queries and ordered traversal efficiently. Heap trees are advantageous over maintaining priority queues with efficient insertion and deletion of this complexity of order of log of n. Hash tables are fast for direct access, that is order of 1, that is an average, but they do not naturally support priority based operations without additionally structure like heaps. Heap trees are especially useful for dynamic collection with changing priorities, offering efficient insertion and deletion and retrieval with complexity of order of log of n. Arrays have constant time indexing, that is order of 1, but insertion and deletion can be slower, that is order of n for worst case due to shifting elements. In summary, heap tree are particularly useful for our priority based operations such as maintaining priority queues, finding top k elements and implementing algorithms like Dijkstra and Prim's and other algorithm. Other data structures excel in different scenarios such as balanced tree for ordered collection, hash table for direct access and linked list for dynamic resizing. The choice of data structure depends upon the specific requirements and constraints of your problem. Heap trees in real life. Heap trees, especially binary tree, may not be directly encountered in every life in the same way that you might encounter everyday objects. However, the concept of underlying the heap trees have numerous real life applications in various domains. Here are some ways the concept of heap trees are applied in everyday scenario. The first is transportation network. The traffic management systems use priority queues often implementing using heap tree to optimize the traffic flow by adjusting signal things and managing the congestion in real life. Second applications we can apply this heap tree is air traffic control. The air traffic controller use priority based algorithm to manage aircraft's takeoffs and landing sequence, ensuring safety and efficiency. The third application is emergency room triage. Hospitals are priority queues to determine the order in which the patients are treated in an emergency room based upon this severity of their condition. The fourth application is online shopping. E-commerce websites are use priority queue to manage the order fulfillment and shipping, ensuring that this high priority orders are processed quickly. The next application, computational biology. In genomic research, algorithm based on this priority queues help identify this high priority genetic sequence for analysis, diagnosis and drug development. Next application is search engine. Search engines employ priority queues to determine the relevance and order of the search results based on the factors like popularity, relevance and their user preferences. The finance. The stock trading systems utilize priority queues to manage and execute orders based upon varying priorities such as limit prices and urgency. Next application is network routing. Network protocols use priority based algorithms to route data packets efficiently across the network to minimize the congestion and latency. Resource management. Cloud computing services use priority queues to allocate resources to virtual machines or tasks based upon their user defined priorities. The next application we can apply is streaming services. The content delivery networks use priority queues to optimize the distribution of multimedia contents based upon the factors like user location and demands. While heap tree themselves may not be directly visible in everyday life, their underlying principles are applied in wide range of technologies and systems that we interact with on regular basis. These applications demonstrate the importance of this efficient priority based operations and their impact on enhancing efficiency, responsiveness and the user experience in their various domain. I must conclude with this session by saying that in conclusion, heap trees, specifically binary trees, are fundamental data structure that plays this vital role in computer science and various real world applications. Their ability to efficiently manage priority based data makes them a versatile tool for solving wide range of problems, from priority queues and graph algorithms to event scheduling and data comparison. Heap trees offer a powerful way to maintain and process elements based upon their priority or value. As we explored this throughout this presentation, heap trees provide efficient operations such as insertion, deletion and retrieval of highest and lowest priority elements, and the logarithmic time complexity for these operations as well as their suitability for dynamic scenario make them like very good algorithm or very good data structure where efficient priority management is crucial. In today's this interconnected world, the concept of underlying heap trees have been applied in diverse fields such as transportation, healthcare, finance and many more. By understanding the principle of heap trees and their applications, we gain the insights into inner working of technologies that shapes our daily lives. As we continue to innovate and address complex challenges, heap trees stand testament to the enduring the importance of data structure and algorithms in driving technologies of and different process. So, with this I thank you all. Thank you.